So now we're getting into more of the aspect of this chapter, colligative properties. And so here for colligative properties, it's not necessarily the identity of the chemical, meaning we don't necessarily care if it's polar or non-polar. We mainly care about how many particles are in solution. So for example, when you dissolve, say, or not dissolve, when you mix methanol in water, for every mole of methanol, or whenever you dissolve methanol, you just get one particle equals one molecule. So the molecule doesn't break apart. So however many molecules or moles of methanol you have, it still remains one entity. But on the flip side, if we have something like sodium chloride, if we had 1 mole of sodium chloride, that would be 2 moles of ions, which would equal 2 moles of particles. So there will be more particles in a 1 molar solution of sodium chloride, for example, compared to a solution of 1 molar methanol. So for every mole of methanol, you get 1 mole of particles. For every mole of sodium chloride, you get 2 moles of particles. Because remember, when you put sodium chloride in water, it's going to dissociate. And so that does affect the colligative properties. And that's why, as we'll see in a little bit, when you add sodium chloride to water, it increases its boiling point, because now you have more particles in solution to interact with the solvent. And so, as you learned in Gen Chem 1, electrolytes play a key role in colligative properties, and there are 4 colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So to give you an example, a real life example of vapor pressure lowering, we go to the car, and in most internal combustion engine cars, even I think Porsche now, they have radiator cooled. But any internal combustion engine car with a radiator, you have radiator fluid, and it always tells you that when you add radiator fluid to your radiator, make sure you mix it, roughly 50% water, ethylene glycol, which is one of the common components of radiator fluid, in a 50% mixture. And the reason is because when you add the water or the radiator fluid to the water, it helps lower the vapor pressure of the water so it doesn't boil off. Because if you just put pure water into your radiator, the water would have a higher vapor pressure, meaning it could be removed quickly. So when you mix it with radiator fluid, ethylene glycol, it helps lower the vapor pressure, which in turn increases the boiling point. Because if you just put pure water in your radiator, your car usually operates at about 225 degrees Fahrenheit, roughly, and water boils at 212. So you'll just get all steam in your radiator. Not good. Boiling point elevation. An example of this is when you add salt to water. The salt interacts with the solvent molecules, forming ion dipole interactions. These are stronger interactions. It takes more energy to break them, aka increasing the boiling point of your water. Freezing point solution, freezing point depression. An example of this, not so much here, but up north, sometimes in some places they'll take, if it's going to be a very cold night and they're expecting ice, they'll put a salt slurry on the road to help lower the melting point, or freezing point, I should say, of water. Because when you add salt to a solvent, again, you're changing the forces. Now you have solute-solvent interactions, which lowers the melting point or excuse me, freezing point, so that therefore, if water was to fall on the bridge, for example, it wouldn't form ice because you have that salt solution there that helps lower it. An example of osmotic pressure is how they make pickles. So you put a cucumber in a brine solution. Over time, water moves from a region of high concentration to low concentration. So your cucumber has a higher concentration of water. The brine solution is a low concentration of water. So it moves from the cucumber to the brine solution, causing the pickle or the cucumber to shrink into a pickle. The opposite effect would be true if you took a pickle, put it in a water. The water would move from the water container into the pickle to plump it up, so to say. So those are just some examples, and we'll be looking at the different equations involving colligative properties. Now, it does make a difference, as we saw in our example with methanol and sodium chloride, whether we have a strong electrolyte, weak electrolyte, or non-electrolyte. And mainly in this section, we're only going to be dealing with mainly strong electrolytes and non-electrolytes. Now, strong electrolytes are going to be your soluble salts, strong acids, and strong bases. And these completely dissociate in solution. So the number of particles, like I said, is equal to the number of ions. So the moles of your compound would equal the total moles of ions. It's not 1 to 1. It depends on how many ions your compound breaks apart into. And that comes into something called the Hof Factor, which we'll talk about when we discuss non-electrolytes. Weak electrolytes, mainly weak acids and weak bases. We don't discuss much of those in this section. Later on, when we talk about acids and bases, we'll talk about the association of weak electrolytes. Mainly, we look at non-electrolytes. So these are your covalent compounds that don't break apart. So 1 mole of the molecules is 1 mole of particles. And so first, we're going to look at colligative properties with non-electrolytes, and then we'll look at colligative properties of strong electrolytes. And the only difference is we add 1 more variable to the different equations. So first, we're going to talk about vapor pressure lowering, and we're going to keep it strictly to a non-volatile, non-electrolyte solution. So what do we mean by non-volatile, non-electrolyte solution? Non-volatile means that the solvent doesn't contribute, or excuse me, the solute doesn't contribute to the total vapor pressure of the system. So for example, if our solvent is water, that's a non-volatile solvent. If we were to mix it with, say, for example, methanol, that's another non-volatile solute. So that wouldn't have any effect. But now if we go and, for example, we take hexane and we mix it with, say, diethyl ether. Diethyl ether is what we refer to as a volatile solute. And so it's going to contribute to the vapor pressure of the system. And that uses a slightly different law or slightly different adaptation of what's called Raoult's law. And if you take organic chemistry, you'll actually use Raoult's law, which is the law for vapor pressure lowering, for a volatile non-electrolyte solution. So you can see what's the vapor pressure component of each solute and solvent. And then from there, you can calculate the total vapor pressure of the mixture. Now here, we're just looking at the vapor pressure of the solvent. We say that the solute doesn't contribute anything to the vapor pressure of the mixture. And so here it's very important, like I said earlier, vapor pressure lowering. The vapor pressure of the solution is always going to be lower than the vapor pressure of the pure solvent. So if you know the vapor pressure of your pure solvent and you add some non-volatile, non-electrolyte to it, it's going to lower its vapor pressure. So if you start, say, at 100 and you add something to that solvent, it's going to be less than 100. And so the equation we use is P of solvent is equal to the mole fraction of solvent times the vapor pressure of the pure solvent. So this naught sign as a superscript indicates the vapor pressure of the pure solvent. Without the naught sign is the vapor pressure of the solvents in the mixture. So if you know its mole fraction and you know the original vapor pressure of the pure solvent, you can calculate the vapor pressure of the solvent in the mixture. If you want to find the change in the pressure, you can take the mole fraction of solute and multiply it by the vapor pressure of pure solvent. So this is the equation we use for vapor pressure lowering. So the unit of concentration is mole fraction. So anytime we're in a problem, we don't see mole fraction, we have to convert to mole fraction. So now let's take a look at a problem involving Raoult's law. So here we have the vapor pressure of water at 20 degrees Celsius is 17.5 millimeters of mercury. What is the vapor pressure of water over a solution prepared from 200 grams of sucrose and 350 grams of water? So we're at, we're at 20 degrees Celsius. The vapor pressure of the pure solvent is 17.5. So if I was to write this down, we know that pure solvent is 17.5 millimeters of mercury. So that's the vapor pressure of the pure solvent with no solute. Now if we look at our solute is sucrose, which you can see here just contains carbon, hydrogen, and oxygen. So that tells us it's a non-electrolyte. If it was a strong electrolyte, it would be slightly different. So in order to solve for the vapor pressure of the solvent, we need to know the mole fraction of solvent and its vapor pressure of pure water. So this is what we're looking for. What's the vapor pressure of the solvent after we add 200 grams of sucrose? So in order to do that, we need to know the mole fraction of solvent. And once we know the mole fraction of solvent, we know what the vapor pressure of the pure solvent is, so we can find the vapor pressure of the solvent in the mixture. Now there's no particular unit you need to have pressure in. Millimeters of mercury is just fine. So the main crux of this problem is we got to find the mole fraction of solvent. So the mole fraction of solvent equals the moles of solvent divided by the moles of solution. And remember, the moles of solution equal the moles of solute plus moles of solvent. So now in order to calculate the mole fraction of solvent, we need to know the moles of solute and the moles of solvent. So it gives us the molar mass of the solute. So now we have the moles of solute. Now we can find the moles of solvent. So the molar mass of water is 18. So now we have the molar mass of solvent and solute. I'm going to go ahead and add them together, get the, not the molar mass, the moles of solvent and solute. Now I'm going to add them together to get the moles of solution. We get 20. So now we have the moles of solution, we have the moles of solvent. So we can calculate the mole fraction of solvent. So now we have the mole fraction of solvent. We can calculate the P of solvent, or the vapor pressure of the solvent in the mixture. And we get 16.9. So that's the vapor pressure of the solvent after we added 200 grams of sucrose. So in this example, it was fairly straightforward. It gave us the mass of solute, the mass of solvent, the vapor pressure of pure solvent, said what's the vapor pressure of the solvent in this solution. But sometimes, it's not this straightforward. So here, for example, a different type of problem, or it's same type of problem but different initial values. So we're given the vapor pressure of water at 45 degrees Celsius is 71.93 millimeters of mercury. What is the vapor pressure of water over a solution prepared from a 15% mass solution of citric acid in water at this temperature? So notice here, all it gives us is the vapor pressure of water at a particular temperature, and it gives us the mass percent of our solution of citric acid. So first off, what do we know? We know the vapor pressure of pure solvent. So that's something we know. Now, in order to calculate the vapor pressure of the solvent in the mixture, we need to know the mole fraction of solvent and the vapor pressure of pure solvent, which we already know. So if we can find the mole fraction of solvent, we can determine the vapor pressure of the solvent in a 15% mass solution of citric acid. So we're going to need to know the molar mass of citric acid. So let me go ahead and do that real quick. All right. Now the question is now, how do we get from mass percent to mole fraction? And remember, mole fraction involves moles of solvent divided by the moles of solution. So in order to solve for the mole fraction of solvent, we need the moles of solvent and the moles of solution. And again, moles of solution equals moles of solute plus moles of solvent. So we need to know the moles of solute and we need to know the moles of solvent. So we're given the mass percent, a 15% mass solution of citric acid. So we need to make our assumption. So we're going to assume 100 gram solution. So if we have a 100 gram solution, we know the mass of solute is 15 grams. And the mass of solvent is 85 grams. And the way we know this is because we assume the 100 gram solution. So now we can convert mass percent into mass. And now that we have the mass of the solute and the solvent, we can find the moles of each. So 15 divided by 192 and 85 divided by 18. So now we have the moles of solvent, the moles of solute. We can find the moles of solution. So we have the moles of solution, we have the moles of solvent, we can find the mole fraction of solvent. So now we have the mole fraction of solvent, we can calculate the vapor pressure of the solvent in the mixture or in the solution. And notice that the vapor pressure did decrease. So now the new vapor pressure is 70.76 millimeters of mercury. So whenever you're given something other than the unit of concentration you need, you're always going to have to convert it to that unit. So since we needed mole fraction of solvent, we had to take the mass percent of citric acid and convert that using what we learned in the first part of this chapter to convert it to mole fractions. And that's what you're going to have to do anytime you have a colligative property and you notice that the unit of concentration is not what you want, you have to convert it to that particular unit of concentration.